All right, use the table to find a table for the inverse. So we're just switching, you're swapping x and y. So if I was going to draw the table right next door to it, then I'm just switching my x and y coordinates. All right, identify the domain of f. So the domain of f is the x values, and the range of f are your y values. Okay, so that's pretty straightforward. And then the whole point of the second part of this question is that the domain of the original becomes the range of the inverse. So here's our domain. You can see it's now the range. Here's the range of the original, and it became the domain of the inverse. So that was the big issue on this. That was the big idea behind this problem. Okay, evaluate f, the inverse value, when x is equal to 3. So you're going to create an inverse table, or you're going to look at the y value instead of the x value. So you can do it either way. I can create a new table just by switching the x and the y's, and then look at the table that way. X, and then this second row is my inverse, and 3 is the input, so that value coming out of 3 would be 4. Okay, use the graph to evaluate the expressions. Okay, so when this is the original graph here. So here are the points that I'm looking for. On this one here, I'm looking for the y coordinate when x is 1. Now this next one, since it's the inverse, that 0 is actually the y coordinate. So I'm looking for this point. All right, same with C. I'm looking for the x coordinate that belongs with a y coordinate of 7. Okay, so the first one is we just go to x equals 1. And where does it touch the graph? And the y coordinate at that point is 1. So that's the first one here. Okay, the next one is when y is equal to 0. All right, so when y is equal to 0, that would be a horizontal line at y equals 0, which is just the x-axis. Then what's the x-coordinate where the graph touches that? And the x-coordinate is also 0. Okay, C now, to get C, the y is equal to 7. So I go to 7, I draw a horizontal line. That's y equals 7. And where does the graph touch it? What's the x-coordinate where it touches it? Which would be 10. So when you're looking at this notations, guys, when you have a number here, that's asking you to figure out if x is 1, what's the missing y coordinate? Okay, now if you had this, and and this was a 1. Now that 1 is really the y coordinate. What's the missing x? Because of it being the inverse. All right, while a function may not be one-to-one when defined over its natural domain, it may be possible to restrict it so that it is one-to-one. This was the stuff that we did the other day. For the function negative x squared plus 2, decide on a suitable restriction on the domain so the function is one-to-one. And all of them that we've been working on so far have been parabolas. So, and they'll be like that on your test. So where you're going to go is you're going to go to the vertex of that parabola. So if I graph that, I could tell, well, the vertex is going to be 0, 0, but if you're not sure about that, you graph it and you just take a look at it. So my equation is y equals negative x squared, and then it was minus or plus 2, and the 2 is just going to move it up. So plus 2. Okay, so to make this one-to-one, I can cut the domain so it's just the right side that's being graphed, or I can cut the domain so it's just the left side being graphed. Okay, if I want just the right side to be graphed, I can go curly parenthesis, and I want x to be greater than or equal to 0, curly parenthesis. And that gives me the right side of my graph. Right? So that parabola looked like that, and this was the point 0, 2. So the right side of that, out of the choices here, is A. Okay, that's what we would pick. All right, show that x squared plus 2 for x greater than 0 is one-to-one. Find its inverse together with its domain. All right, and then graph the original and the inverse on the coordinate plane with the line together with the line y equals x. Convince yourself that the inverse can be obtained by reflecting the graph of f of x about the line y equals x. So this is what we've been doing. So if I wanted to graph that, I can just type that in, and it'll show me that it's one-to-one. So this is x squared plus 2. So all I got to do is change this a little bit. Okay, x squared plus 2. And right now, if that wasn't in there, I'd see the whole graph. Okay, right now it's not one-to-one because it would fail the horizontal line test. But I can make it one-to-one by either graphing the left-hand side of it, which would look like this, or by just changing this to greater than or equal to, graphing the right-hand side. Either way, that's how I'm going to get my it to be a one-to-one function. So looking at it there, we can see that our y-intercept is 2. That helps us pick out which one of these is correct. All right. So out of here, we know it can't be those two because it's the whole graph. All right. And we got C. That looks like it goes through 2, and so does that. So how do you differentiate between C and D? So the way that we can tell that they're different is this one is using a vertical line test. Vertical line test. This one is showing the horizontal line test. And the horizontal line test is what we use to tell if something is one-to-one. So this guy here passes the horizontal line test. Therefore, it is a one-to-one function. All right, then the next step was find the inverse. Okay, so that's where we switch, we write it like this, and then we switch x and y, and then we solve for y. And there's our solution there. Okay, the domain of this function, its domain, would be that expression has to be greater than or equal to 0 because it's under a radical. So when I add 2 to both sides, I know x has to be greater than or equal to 2. And this isn't using, I don't think this question asks you to use interval notation, but there it is. All right, so we know our graph here that we're using has to have a y-intercept of 2, so it could be this one or it could be this one. We know it's not those. Okay. Now, it's got to be symmetric with respect to the line y equals x. Okay. So we know it's going to be A because the D is not symmetric, and if we wanted to see, if we just wanted to graph it on Desmos and see what it looks like, y equals square root x minus 2, and there it is. Here's the line y equals x, and then you can determine the solution that way too. Some values of a invertible function, that just means it has an inverse, are given in this table. All right. The question is asking what is the inverse value when 4 is the input. So one way you can do that is create a new table by just switching the x and y coordinates. And now if I'm looking for the value for 4, 4 gets sent to 5. All right, use the graph to find the following. So on this first one here, we did one like this earlier. When I see that notation, that 4 is really the y coordinate. That negative 4, because this is the inverse. Okay? So if I don't have, I could graph the inverse and then treat negative 4 as the x coordinate, but I have the graph of the original here. So if I wanted to read this using the original graph, I'm really looking for where does this line cross our graph? That's the line that I'm drawing to answer this question. Okay, and then this would be the missing x coordinate. So 2, negative 4 answers that question. Okay, now the next one, if I'm thinking about this without having the inverse drawn, I'm now looking for the x coordinate that has a y coordinate of 1. Or a 4, I'm sorry. So I would draw a line right here for 4. And I'm going to use that horizontal line to answer this question. The x coordinate that has 4 as a y value is 2, negative. And then the last one, since that's an inverse, then 0 is the y coordinate. And that's the horizontal line that I would draw to answer this one, and my x-coordinate is also 0. All right? So, if these problems look like this instead, with a f instead of the inverse, then the negative 4 would be the x values instead of the y values. And you would be looking for the missing y values. When they're inverses, the numbers in here are your y values, and you're looking for the missing x values. All right. Graph a one-to-one function that meets the criteria. Okay, so we know that the domain is from 4 over. All right, so it's going to be 4 to infinity and include 4, so I know it can't be that. Okay, so it could possibly be, looks like these three. Now, when I look at these points, this is the original. Okay, so the original, from that, I know that the point 4, 1, 4, negative 1 is on the original. Okay, this is the original, so I know that the point 5, negative, or 5, 2 is on the original. Okay, now this next one is an inverse. So what that tells me is it's not 7, 6 isn't on the original, 6, 7 is on the original, because that's an inverse notation. Okay, this one's an inverse, so I know that 7, 14, that point is on the original. So then I just look at what graph has those points on it. So 4, negative 1, they all three do, all right? Then 5, 2, okay, 5, nope, can't be that one. And 5, 2 could be this one, so these two would still be in the running. Okay, 6, 7. Okay, over here, 6. That's 6, 6 it looks like. And then the last one I'd be looking for would be 7, 14. So I know it can't be D. All right. And then 19. Graph the one-to-one function that meets the criteria. Okay, so if f of 2 is equal to 9, then the point 2, 9 is on f of x. If the inverse of 5 is equal to negative 2, then 5, wait a minute, yeah, 5, negative 2 is on the, wait a minute, lost my train of thought there. All right, that is the x-coordinate, and that now is the y-coordinate. So when you're graphing this on Math Excel, you're just graphing negative 2, 5, and 2, 9, and since this is a line, you're just connecting the dots then. All right, that's it, folks. This is the second part of the review, and that covers everything that'll be on the test for Chapter 2.